have an invited talk from Jamie Tayar from University of Florida. So take it away, please.
Thank you. Awesome. So I'm excited to be here and to talk to you all because the exoplanet folks, you guys are actually often much more careful than other communities in the work that you do. And so that means that you've done a ton of work to take many, many spectra and process them very carefully, to look at your light curves and take care of all sorts of systematic issues. And so then you get to the point where you have all of your planet properties measured relative to your stellar properties, and you come to the stellar folks with a list of requests. You need things like a temperature, you need a luminosity, you need a radius, you need a composition, you need a mass, and you need an age for that star. And as Dan and some of the earlier talks have already told you, we have uncertainties on the stellar side that we need to make you all aware of, because your careful work is getting to the point where the stellar uncertainties start to matter. It's not those planet uncertainties that are dominating your error budget, it's often the stellar uncertainties. So as Dan mentioned, you probably have a stellar luminosity uncertainty of something like 2.5%, a stellar temperature uncertainty of something like 2%, and a stellar radius uncertainty of something like 4%. And if you're using a composition of the star, there's some systematic uncertainties in that composition at kind of the 0.1 or 0.15 dex levels. But then, okay, Dan has talked you through how all of that works. Now you need a mass and an age for your star. So how are you actually getting those? The simplest way to explain how to get a stellar mass and a stellar age is that you take a set of known stellar parameters, maybe that's a temperature, a luminosity, and a metallicity, and you look up what the answer for the stellar mass and age is in a grid of models. So when we model a star, we make some very nice simplifying assumptions. We say the star is spherical. We assume things like conservation of mass, conservation of energy, hydrostatic equilibrium, so we're balancing pressure and gravity. We take care of all of the nuclear fusion and taking care of the energy generation and the energy transport. That gives us a set of couple differential equations that are all based on the physics of stellar interiors. We put that into some sort of stellar modeling code, and we can say, okay, for a star of some mass, maybe one solar mass, some composition, say solar composition, and maybe some initial rotation or other parameters, we put it into the modeling code solves those couple differential equations, and out comes a prediction of how a star of that mass and composition should evolve over the course of its life. So you solve the set of equations, then you say, take a step forward in time, how does it change? And you can map out that track across an HR diagram as a function of temperature and luminosity. It starts as a main sequence star, it evolves across the subgiant branch, it goes up the red giant branch. And so that means that people like me who run those stellar models can do this for a range of masses, say 0.6, 0.7, 0.8, 0.9, 1.0, all the way up. And then you take your star that you have carefully characterized and say, okay, well, I know that the stellar temperature is this plus or minus this, and the stellar luminosity is this plus or minus this. You draw that very tiny box on this diagram of all of the models that I've run, and it will tell you that the mass of that star is 1.04 plus or minus 0.03 solar masses. And that sounds great. That's what you needed. The problem is when I explained how this process worked, I skipped over the bit where it says it has some physical assumptions. And that is hiding all sorts of uncertainties that usually you wouldn't have to deal with. Some of these are measurable things. What are the nuclear reaction rates? What are the opacities? Those are physical things that physical systems people measure. They have an uncertainty. We take them in as a table. We pick some value and we propagate that forward. Did we perturb that value for you? And if so, does it matter for the predictions of the models? This also includes all of the radiative processes and atmospheric structure. We're trying to measure a stellar interior, but this is actually a boundary value problem. And if you remember from quantum mechanics, changing the boundary conditions of a boundary value problem changes the whole solution. And so that's going to change your results. We are parameterizing all of the fluid dynamics and convection in this one-dimensional spherical model. What is one-dimensional convection? No one knows. We put in some number, and then maybe we did the rotation and all of the mixing. Maybe we just turned that off and said it wasn't important. And that's not like the only list. If you look at one of these MESA models, if you've ever opened up the box of all of the input numbers that you have to put into a model like that, it is a very long list of choices that people made. And the reason that you care about this is because of how it affects the results, right? I said for TOI 141, when I put it into this grid of models, I got 1.04 plus or minus 0.03 solar masses. But if you had put it into a slightly different grid of stellar models, which looks very topologically similar, you might have gotten 1.07 plus or minus 0.02 solar masses. Those are technically concordant, but it doesn't feel good. So, depending on where your star is, if you're doing something like a giant planet around a more giant star, it may change more or less. Different stars in different parts of this diagram are going to shift. And you can do this parameterization for not just one or two grids of models, but for many grids of models. You can do it mapping across the position of the HR diagram. You can do it at different metallicities. And you can make up a map of how uncertain do the model choices that you make. And these are real model choices that people who have published actual model grids have made. How much of a difference in mass is that? And in many cases, it's 2, 3, 4, 5%, and sometimes up to 10%. And so that means that if you just run your numbers through some grid of models that you found on the internet and somebody made a nice parameterization and tool for, you are not accounting for this uncertainty. That is really a stellar uncertainty, but matters for you as well. And you can do the same process for what is the offset in ages between these models. And it is 10, 20, 30, 40, 50, cough, cough. We just capped the top at 50%. And depending on where you are on the HR diagram, if you're very close to the zero-age main sequence, changing that luminosity a little bit changes your age by a large fractional amount. If you're pushing closer to the giant branch, it's really uncertain up there. For this original paper that I wrote, we just said, oh, the giants are bad, but you probably don't care. So just don't look over there. But actually, I have a really talented graduate student who's been doing this for the giants properly. And she has mapped out just how bad it gets. Her scale goes up to 90%. So depending on whose model you use, if you pull a temperature and a luminosity and a metallicity from whatever you've characterized and grab a model, you can get an age difference of 90% on the giant branch. So that's great. And so that means that when you're thinking about the mass and age uncertainties of your stars and therefore of your planets, there are two different things you have to consider. One is the model-to-model systematics that the stellar people have not fixed for you. And one is properly propagating your empirical uncertainties, which generally this community is very good at. And when you're thinking about the empirical uncertainties, that's also going to depend on where you are on the HR diagram, right? Because if you measure a star that is, say, over here, it's got a small uncertainty in luminosity because you've got Gaia and it's wonderful. You've got some reasonable uncertainty on temperature, however you got that, photometric, spectroscopic. When you think about the uncertainty on the mass and age, in kind of the subgiant branch, those models are separated by a lot. And so the difference between a 1 gigayear model at the top and a 5 gigayear model in the middle is huge. And so your empirical uncertainties probably don't matter that much. But if you're working on the main sequence or near the main sequence turnoff, those kind of G and F stars, those models are pretty close together. And so the same amount of empirical uncertainty becomes a larger empirical uncertainty on the mass and the age. And similarly, if you're working on the giant branch where all of those models collapse together, again, those uncertainties on the mass and age are going to be larger. And for the giants, Leslie has gone through and said, okay, where does the empirical error dominate versus where does the theoretical error dominate? And for the giants, as you go more luminous, it's a theory problem. As you get towards that subgiant branch where the models are well separated, it's an observational error problem. And you can imagine doing the same thing for the dwarfs. And so that means depending on where you are on the HR diagram, which of these is going to matter the most will change. In general, you should assume there's probably model-to-model systematics of about 5% in age and about 20% in mass, and probably empirical uncertainties from propagating your uncertainties on your temperature and your luminosity that are of a similar size. And so you want to make sure you're accounting for both in your problem. And that's cool. That allows you to characterize what your uncertainty is now, but that's kind of a high uncertainty for all of the careful work you put in to characterize your planet. So how do we make this better? Right? So where we have observational uncertainties that are dominating, how do we get better observations? And then as in other places, how do we fix this as well? So when we're thinking about places where the observational error uncertainty dominates, we've been thinking about how do you actually characterize what your luminosity scale is? What is your absolute flux that you're getting for a star? And so you've heard mention of Landolt already today, and you'll hear about it again later in the week. The plan is basically to put a box of lasers in space, shine them down on the ground. We know exactly how many photons are coming out of the laser, and therefore we know exactly how many photons we're getting from the star next to it. We can map out the relative brightness and calibrate that absolute scale. And then we have the correct number, which we can propagate forward both for those individual cases and for calibrating the models. And we think that these absolute flux improvements for Landolt are going to cascade down to a luminosity improvement, a temperature improvement, a radius improvement, and a mass improvement, which then all propagates to your improvements in your planet parameters as well. So that's great, that fixes the observations, but there are many places where the observational errors are not the only issue. So how do you get around these floors? Because I've quoted you these numbers and you saying like you can't do better than this if you do it this way. But you don't necessarily have to do it this way. Sometimes you can be clever because you are not using stars that we don't know anything else about. You have more than a temperature and a luminosity and a metallicity. So if you have a transiting planet, the properties of that transit will tell you something about the stellar density. You've heard about that already. And sometimes, if you take that stellar density estimate and the mass uncertainty from the models, which is 5%, but if your transit density is really good, that may give you a radius for your star that is better than the radius you would infer in L plus T, absorbing the systematics of that case. And if you have a really good radius and a really good luminosity, then you have a really good temperature. And your log G uncertainties are going to be small. And so there are places where if you have a well-characterized transit density, you can do better kind of going around the problem and keeping count of all your uncertainties when you do that than you can by doing it directly in the simple way. Similarly, and it's not just the transit density that you get, right? From a transit, you get the planet period, the transit depth, the RV semi-amplitude, the transit duration, ingress and egress duration. All of those things are telling you something physical about the star-planet system. And some of them can be combined in clever ways to estimate the mass and the radius of the star. And so if you're careful with your system, sometimes you can do better using those purely empirical constraints than you can going through the models, because the models have these underlying uncertainties that make it hard to beat. And people who work on MDORFs are probably pretty familiar with this kind of situation already, because you've probably been ignoring the models for a decade and using the relationships from Andrew Mann, because the models in the MDORF regime are horrifyingly bad. It turns out Gaia gives you the opportunity to do those sorts of calibrations. What is the empirical location of the stars on the main sequence for not just M dwarfs, but for F, G, and K dwarfs as well. And so depending on where you are on the HR diagram, you may be able to calibrate your relationship between surface brightness and the Gaia colors to something that gives you a radius that is comparable to or better than what you would infer from doing the standard L plus T propagation. Similarly, on the age side, there are also tricks you can play with the ages. right? We've heard a little bit about gyrochronology already and how stars slow down over time. It is possible to map out how precise your age is from these kind of isochrone-based methods versus how accurate your age is going to be from something like a gyrochronology as a function of stellar luminosity and stellar effective temperature. And what we find is there are many regimes where the age you get from gyrochronology, even taking into account all of the uncertainties that you heard about earlier, may be better and more precise and more accurate than the age you would nominally infer from the models. And so if you're working in kind of the K to M dwarf regime, those model ages are really hard and really uncertain. So you may actually do better using the rotation and the gyrochronology to give you some estimate of the age. And that's not something that's going to stop being true, because we have rotation periods now from the ground, we have them from Kepler, we have them from K2, and we have them from TESS. But we're also going to be getting those for Roman. And so if you're thinking about your planets that you're going to find around Roman, we expect to get something like 300,000 rotation period detections out of Roman. It's not going to be every star. There's some mapping of how detectable they are. It's going to be the brighter end. But that's often where you're going to be finding the planets as well. And so for a lot of those stars where you may not be able to take a careful spectrum, or you may not be able to get such a precise luminosity and temperature, you may do better getting your planet and star parameters from something like gyrochronology than you would in other ways. Okay, so that is how do you fix the observations and how do you get around the problem? But what about these places where the theoretical error dominates, right? Right now, when I've been quoting you these theoretical errors, I've been assuming that everybody in the world's model is equally good. That's a very uncontroversial stance to take, but it's probably not true, right? Models are defined for certain regimes where they've been carefully done for certain types of stars. And then once I have used them for my project, I throw them on the internet and people can use them for anything. So how do we figure out which model is best? And I think the answer to that is thinking about what stars we have characterized really well, where we can compare the properties of a star to the properties of the models. So we start with the sun. There is a quoted temperature and a quoted luminosity for the sun. And you might ask which model grid goes through the sun's luminosity and temperature at the solar age. That's where the dots are. The answer is none of them. So that's great. Okay, but we don't have to stop with the sun. There are other stars where we've characterized really well. You've heard a little bit about astroseismology already, right? So these are stars where we have a seismic mass, a seismic surface gravity, we have a temperature, we have a luminosity, we have a radius, we have a composition. And we can put them into the models and say, okay, for a star of this mass at this surface gravity, what is the difference between the temperature I actually measure for this star and the temperature I predict in the models? The answer is the difference is 100 degrees or something, whatever. And you can play that difference for multiple different model grids and say, is one of them better? The answer is no, they're all sort of equally bad. These are kind of on the subgiant regime as we kind of push down towards the dwarfs. So that's great. Okay. What else? What other stars have we characterized really well? So eclipsing binaries, right? If you're working with an eclipsing binaries, you have some empirical measurement of the radius, the luminosity, the mass, the temperatures, the composition of the system. You can say, all right, I'm going to force my models to go through one of these stars, which has very tiny observational uncertainties, and then say which one goes through the other star at the same age. The answer is, again, none of them, which is great. That's telling you there's something physically wrong with all of these models, at least at the level that you're starting to be able to measure the empirical data. And it's not just the sun, it's not just the astroseismic giants, it's not just the eclipsing binary stars. You can do this for open clusters. Open clusters are great calibrators. They all should have the same age, the same composition. We know them extremely well. People have been studying them for decades. So let's take the stars that we have observed at M67. We have a temperature, we have a surface gravity, we have a metallicity. Let's plug them into the models and ask what the age is. That's the color coding of the points, and then we've kind of, Susie has plotted some of the tracks for what the models, the isochrones should look like. When you hear about cluster ages, people are usually doing that here at the main sequence turnoff, where the models are very sensitive, you can estimate the age quite well. But if you are not working at that regime, you will start to notice that the models kind of drift off from matching the cluster points. And that's telling you again that there is something physical in these models that is not correctly matching what is happening in reality, and therefore you have to be careful when you use these models outside of this regime in which they were calibrated. And you can take it a step further, say, okay, not just clusters, not just binaries. What about binaries in clusters? If there's anything we know, it's binaries in clusters. And again, you take the combined point, you break it into the individual points. There's some uncertainty on that, but it doesn't really match in quite the level of precision you would like, which is unfortunate. But we know that this can be done better, because when people do this very carefully for individual clusters, they look at the whole shape of the HR diagram, especially at the main sequence turnoff. They do careful analysis. They try all of those pieces of physics that we know are uncertain in the models, everything from the composition to the mixing length to the nuclear reaction rates. You can actually make a model that will match the cluster and gives you an uncertainty on the age of about 5.5%. And so it is possible to do this model calibration. It just hasn't been done correctly yet. And now that we have so much more data, we're thinking about how do we actually generate a grid of models that's going to use these calibration systems and match those stars where you know what the right answer is, right? Because we have all of these different physical choices we can make in the modeling, but we also can map out what the consequences of each of those physical choices is, and therefore which ones need to be used to match the properties of the actual observed stars that you have characterized in the regime that you have characterized them. And so we can start thinking about, is there a way to create something like an empirically calibrated grid of stellar models that you can use until the stellar physicists figure out what's going on over there? And so that's one of the things we've been thinking about, how to do that in such a way that it's going to be useful to you. But until that's been done, you should check the grid of models that you are using in the regime that you are using it, and make sure that it looks right. Because you're starting to ask questions that depend not only on precision, but also on accuracy. When you're starting to think about things like what is causing the physics of the radius valley, you can no longer absorb that systematic shift. You want to know, is it a match to core-powered mass loss, or is it a match to photoevaporation? And if you're thinking about the dynamics of systems and how that's shaped the evolution of the system over time, right, you need an actual age for that system. And you need not only the relative ages to be right, but the relative ages as a function of metallicity and the absolute ages, which will tell you something about the time scale of these sorts of processes and how they've evolved in different planetary systems. And similarly, if you're thinking about composition and habitability and how the different relationships of different chemical elements will affect things like the possibility of plate tectonics, we know that those ratios of chemical elements have changed over time. And so that's another place where you're really going to need an age that means something if you want to think about how the details of habitability are starting to evolve over galactic timescales. And so what I want to caution you is that there are still significant uncertainties, both observational and theoretical, on host star properties. There's a lot of different avenues where we're starting to have the data to improve on those, both on the observational side and on the theory side. But that there may be cases where not just doing the standard error propagation, but by using some additional information you have on the system, you might be able to do better than the sorts of numbers that you usually get quoted about what your uncertainty floors should be. But that when you do that, you should be very careful about propagating your errors. So I'm going to stop there and ask if there are any questions.
Awesome. Thank you, Jamie, for a great talk. So we have some time for questions now. And again, definitely encourage questions from early career people in particular.
Yeah, thank you for a nice review talk. It was very worrisome for someone who doesn't do stellar astrophysics. One question that I had is, you mentioned that for some of these clusters, people doing this very carefully were actually able to kind of tweak all of these inputs and get a good match to the observations. And I was wondering if you had a sense of which things matter most when they did that, like what did they have to tweak specifically?
Yeah, so this is currently my favorite paper. It was written by Martin Ying, who's a graduate student at Dartmouth. And he actually went through and did exactly that parameterization you were checking. For M92, which was what he was working on specifically in this paper, it was the distance to the cluster that was actually the most uncertain thing. But once you took care of that, then you started getting into exactly what composition you were using, and then what you were doing about helium and diffusion, and only then did you start getting into things like the nuclear reaction rates and the mixing length. Mostly because what he was doing the calibration on and where most of the stars are is kind of this main sequence turnoff, which becomes very sensitive to the helium and to the composition. Yeah, good question. And that will be differently true depending on where you're doing the calibration.
Thank you very much for the talk. It was really, really interesting. I am Fede from University of Birmingham. Talking about this fitting the model to the data and now it works. How much of it is actually the model being good and a couple of tweaks in the parameter that are needed, and how much of it is like brute force in it to do what you want it to do? And actually the model not being correct.
Yes, that is a great question. I think the answer is right now we can brute forces, but we cannot do it correctly. I don't think we know enough about stellar interiors physics and how to generate a model in one dimension that correctly parameterizes everything that's happening in 3 dimensions to do this correctly with the correct physics. If you put in the correct physics, you get the wrong evolution. And so I am kind of advocating for and getting people to consider the possibility of making models that we know are physically wrong, but give you the right answer that you can use until we get our stuff together on our ends. Which sounds horrible, and I think the model people hate it, but they're not here, so it's fine.
You've suggested that imperfections in stellar evolution models are responsible for many of the issues you've described. How can you be sure that the issues are not associated with the spectroscopy-based T-effective and log-G or luminosity inferences that are often used as inputs to the mass age inferences themselves?
Yeah, I think that's a real question. And to do this properly, you have to be very careful about where each of your data points is coming from. Kind of each of the tests that I showed you is using a slightly different where did they get their temperatures and their gravities and their metallicities from. And these issues show up in similar ways in a lot of those different tests. So it's not just one error that we're doing. And we're able to do cross-checks where we know that the temperature scale can't be off by more than about 1% from the various different combinations of things. And so I think that means there is something there's something wrong with the models. When we do the calibration, we have to be very careful about where we get our data from and make sure it is done homogeneously, because otherwise you will build these horrifying systematic errors into the model calibration. But I think there's really a model issue as well. Just keep talking. They'll turn you on.
Yeah. Oh, JJ Zanazzi, UC Berkeley. I'm really interested in this result that you have constraining the presence of plate tectonics in planets. Is the idea that if plate tectonics is happening, you basically cause metallicity mixing in the planet, and by measuring the metallicity, you can constrain whether it's occurring or not?
No, it's much simpler than that. We aren't going that far, because I think that requires much more detailed knowledge of the planets. What we are trying to say is if you ask a geologist about what is required for plate tectonics, you need a magma with a certain viscosity. As you change the chemical relationships in that magma, you will change the mineralogy and therefore the viscosity. And so if you want to have magma that flows, you need some relationship between silicon and magnesium that's within some regime. And that regime gives you some, Mg to Si relationships We can take that from stars, from galactic chemical evolution, and say, do the stars that exist in our galaxy, are they in the regime where plate tectonics is even possible? Or do we have to worry about the exact details? And the answer is right now, most stars have relationships that tell you that plate tectonics is possible, but it's actually getting less and less favorable to have plate tectonics over galactic time. And so it may be that sometime in the future, many planets will not have that, that option. Awesome.
Amazing. Unfortunately, we're out of time for questions, but let's thank Jamie again.